Hello. So in this video, we're going to be talking about using the Laplace transform to solve an ODE. So the Laplace transform is really useful in that we can actually solve an ordinary differential equation using the Laplace transform. And there's really two basic formulas that we need to know. We need to know that the Laplace transform of the first derivative of a function f of t is s times capital F of s minus f of 0. And capital F of s, sometimes it's referred to as big F of s. But it's basically the Laplace transform of f. So basically Laplace of f of t. That's what big F of s is. So I'll call it big F of s. And the Laplace transform of f double prime, the second derivative of f of t, is s squared times big F of s, which is, of course, the Laplace transform of f of t, minus s times f of 0 minus f prime of 0. So that's the derivative of the first derivative of f of t evaluated at 0. And we write here f of s is the Laplace transform of f of t. So we can use this to our advantage when we're given this second order ODE, y double prime minus 4y prime equals 2e raised to the 3t minus e raised to the negative t. And we're given these initial conditions that y of 0 is equal to 0 and y prime of 0 is equal to 0. And the first thing to realize is that we're going to use the formulas for the Laplace transform of the derivative, but recall that instead of y, we have f. So y prime, or y of t, is really the same thing as the f of t in our formulas, but they're just different letters, but it's the same concept. So step one is to take the Laplace transform of both sides of the equation. And so basically, this should be equal sign there. So basically, we're going to take the Laplace transform of this portion here and of this portion here. And we're going to end, and this is this step here, Laplace of y double prime minus 4 times the Laplace of y prime is equal to 2 times the Laplace of e raised to the 3t minus Laplace of e raised to the negative t. And this is all using linearity. If you notice, we're breaking up each individual transform, and so that we only have to focus on just, like, for example, e raised to the 3t, e raised to the negative t, here y prime, and here y double prime. So using those equations that we have above, we're actually going to transform y double prime into the equivalent form in the Laplace domain. So that's going to be s squared times big Y of s, instead of big F of s, we'll say big Y of s, minus s times y of 0, instead of f of 0, it's y of 0, minus y prime of 0, instead of f prime of 0, it's y prime of 0. And then that's for the second derivative. We use a second derivative equation here. And in here, we use the first derivative equation. So this is 4 times, remember, it's 4 times the Laplace of y double prime. So that's why it's 4 times this entire thing. So that's s times big Y of s minus y of 0. And from here, if you notice, we actually we take the inverse Laplace transform of e raised to the 3t, which is 1 over s minus 3. I'm sorry, the Laplace transform of e raised to the 3t, which is 1 over s minus 3, and minus 1 over s plus 1, which is the Laplace transform of e raised to the negative t. Okay, so the second step is we're going to use this information, and we're going to use the initial conditions. Y of 0 is equal to 0, and y prime of 0 is equal to 0. And remember that these are showing up in, we'll circle these here, these are showing up y of 0, y prime of 0, y of 0 here in the equation. And so we have to apply the initial conditions. Fortunately, in this problem, we have y of 0 is equal to 0 and y prime of 0 is equal to 0. So the problem becomes a little bit more simplified because we can eliminate these terms that have the y of zeros or y primes of zeros because they're going to be all 0. And applying in the initial conditions, we get this term here. And then the goal in step 3 basically is to isolate y, big Y of s. So we're going to factor y of s out. We have big Y of s times s squared minus 4s equals 2 over s minus 3 minus 1 over s plus 1. And then we're going to divide over the s squared minus 4s, so we're going to end up with these two terms here. Now, it's important to realize that actually the inverse Laplace transform of big Y of s is y of t. And that's what we want. We're looking for y of t. That is the solution to the ODE. So, in fact, the next steps, although they're not going to be so simple, once we find the inverse Laplace transform, we're actually done with the problem. And so this is the beginning of step 4. Now, with these terms, they're actually, we can tell they have factors, so we're probably going to use a partial fraction expansion. In fact, we are, because they're not directly found from an inverse Laplace table. But we have written here the inverse Laplace of big Y of s is equal to the inverse Laplace of the right-hand side, which we break up here into two terms. We say term 1 and term 2. Due to the linearity, we can do that. And here we, just to be a little bit organized, we're going to try to work with each term individually and then combine the results at the end. So in step 5, we're going to work with term 1. So term 1, we're considering 2 over s minus 3 times s squared minus 4s. And what we can do is actually, we're going to factor, so we have s minus 3, that's one factor, it can't be factored anymore. S squared minus 4s, well, that can be factored into s times s minus 4, so we do that when we're using partial fraction expansion. And we'll notice that each factor has a real root. So we're going to do use just constants a over s, b over s minus 4, and c over s minus 3. And in the typical way that we solve for the constants, right, we try to, first of all, we multiply this entire, this s times s minus 4 times s minus 3 to the right-hand side. We end up with this big equation here. And then we have these three conditions, right? Let s equals 4, let s equal 3, and let s equal 0. And that's in order to find a, b, and c. And we've seen how to do that before. We get b is 1/2, c is negative 2 over 3, and a is 1 over 6. And so we just plug those into our term 1. So our term 1 turns into 1 over 6 over s plus 1 over 2 over s minus 4 minus 2 over 3 over s minus 3. And in term 2, we end up with 1 over s plus 1 times s squared minus 4. It's a similar thing. We factor s squared minus 4s. We realize that it's s times s minus 4. And we notice that the entire denominator, or each factor in the denominator, has real roots, right? Real root of s is 0. Real root of s minus 4 is 4. Real root of s plus 1 is negative 1. And of course, the roots are the values of s that make the term equal to 0. So we just use constants, right? A, b, and c. And of course, in the similar way that we did in step 5, we let s equal to 4 here, at s equal to negative 1, and s equal to 0. And the goal is just to find a, b, and c. So we get term 2, negative 1 over 4 over s plus 1 over 20 over s minus 4 plus 1 over 5 over s plus 1. All right. So in step 7, we're going to combine the results from steps 5 and 6. So these three terms are from step 5, and these three terms are from step 6. And we notice we have some common denominators, so we add everything together, right? Like 1 over 6 over s, 1 over 4 over s, and then this s minus 4 term, s minus 4 term here. So we add everything together. And now in step 8, we're just going to find the inverse Laplace transform of big Y of s. So the inverse Laplace transform is the inverse Laplace transform of this past step 7. And we can factor out, this is why it kind of helps to factor out all the constants, because we can see, well, I'm going to pull out the 5 over 12. I'm going to pull out the 9 over 20. I'm going to pull out the negative 2 over 3. I'm going to pull out the negative 1 over 5. And you just work with inverse Laplace of 1 over s, which is 1. Inverse Laplace of 1 over s minus 4, that's e raised to the 4t. Inverse Laplace of 1 over s minus 3, that's e raised to the 3t. And inverse Laplace of 1 over s plus 1, that's e raised to the negative t. And you have all those constants being multiplied there. And so our final y of t is, in fact, 5 over 12 plus 9 over 20 e raised to the 4t minus 2/3 e raised to the 3t minus 1 over 5 e raised to the negative t. So this is the solution to the ODE, and this is the solution to using the initial conditions. So this is how to find the solution of an ODE using the Laplace transform.